Okay, so in this video I'm gonna show you how to draw 3D cube on the character display. Yeah, you hear me right, 3D cube on the character display. And not just one character display, but pretty much any character display that you can get. That includes the old but great looking VFD display, the newer but horrible looking LCD display, LCD displays that actually look kind of decent, and finally the best looking one, which is the OLED display. So let's get started. And I will start with one of my older projects, because I already have the video how to draw 3D cube on the OLED display, so that will be a great starting point. Now what I want to do is draw the same 3D cube, but probably much smaller on the character display. However, there is one small problem, and that is that we cannot control individual pixels of the character display. The Arduino just sends which characters to display, and then the display controller will look into its own memory and decide which pixels to light up. That said, if you've seen any of my other videos with character displays, you probably know that we have a little bit of freedom. And that is, we can define up to 8 custom characters, meaning the pixel content of those characters. So here is the game plan. We will draw the cube on the OLED display small enough to fit into the area of 8 characters, that is 4 by 2 characters. We will get the pixel content from the buffer, and based on this content, define 8 custom characters. Finally, we will draw those 8 custom characters to the character display. And since all my character displays that I'm using today has the resolution of 16 by 2 characters, in order to avoid a lot of empty space, we will just repeat those 8 custom characters 3 times, and that will result in having 3 animated cubes on the display. Before we actually start writing the code, let me talk about the sponsor of today's video, which is a PCBWay. And not only you can get PCBs, but also 3D printing, CNC machining, and all the other kinds of manufacturing. And if you use the link down in the description of this video, you can get 10 PCBs for free, only paying for shipping. So thank you PCBWay, and let's get back to our video. So here is the rotating 3D cube project running in the browser using the Walkway, which is a free online Arduino emulator. And the first thing we want to do is to convert it from using the U8G library, the older one, let's call it U8G1, to using the U8G2 library, which is a newer version of the library. And the main reason for doing so is because inside the U8G2 library, we can easily access the frame buffer. Thankfully, I already have the video how to do that. It's called the U8G versus U8G2, and it describes the process of how to take a project for the U8G1 library and convert it to using U8G2 library. Obviously, I cannot force you to watch all my other videos, but if you want to know all the details, I would highly recommend to do so. There is also a Walkway project for this video, and it's this menu. So what we will do is we will borrow a few pieces of the code from this project and apply those changes to the 3D cube project. As a first thing, we need to go to the library manager and include the U8G2 library. Not quite sure what this error means, but if I click retry, it seems to be fixed. Go back into our code, and from this project we will say include U8G2 library instead of including the U8G1. Then we need a constructor, which is this line, and it's actually different from the U8G1 library because for U8G1 we were drawing the content by individual pages. Now it's using the full frame buffer. So I'll copy this line into our code instead of those initializations. And since this is called U8G2, we have to replace all the U8G1 occurrences with U8G2. So I'll search for U8G dot, and you can see we have all of those down here for drawing, and replace those with U8G2 dot. And click the replace all button. The next thing that's required for U8G2 library is called the begin function. So in here I will search for the setup function, which is here, and copy the U8G2.begin, and again paste it into the setup function just before setting the color. And we need to slightly adjust the drawing loop. So again, previously we were drawing the screen by pages, which is this first page, this loop, and calling the U8G next page. Now we are using the full frame buffer, so the Arduino is storing full frame buffer in its memory, and then we are updating the whole screen, which means that we need to use different functions, and that's for clearing the buffer, which is this U8G2 clear buffer, so this one. And in here I'll get rid of this first page and this loop, and before drawing anything I will clear the buffer. And after we draw everything, we want to send the buffer to the display, and for that we will use the U8G2 send buffer command. So I'll paste it in here. After we draw everything, I will call U8G2 send buffer. I'm using the draw bitmap p function to draw my logo on the corner of the screen, but unfortunately this function is actually not present in the U8G2 library. However, there is a function called draw bitmap without the p. The p stands for draw bitmap from the program memory, so I can use draw bitmap instead and move the logo out of the program memory. And since this is a very small image, that shouldn't make any big difference. So what I will do is I will delete this program memory and maybe even the constants, so it's just a regular variable. And fingers crossed, if I click the restart the simulation button, hopefully I will see the same result, but now using the U8G2 library. And that seems to be the case. So now we have a rotating 3D cube, looks exactly the same as the last time, but now it's using the U8G2 library. And again, the main reason for doing so is because we want to have access to those individual pixels so we can replicate those pixels on the 16x2 character display. Now those pixels are stored in the buffer not only on the display but also inside the Arduino memory. And if I open the U8G2 documentation, there is a function called getBufferPointer, which will give us the memory address at which those individual pixels are being stored. Now I would assume that the frame buffer starts around here on the top left pixel of the screen, and if you take a look, there is actually nothing going on in here, just black pixels. So I probably want to have something drawn in this corner, so as I access those individual pixels, I can see what's going on. And for that I will use the drawString function and just copy some example which sets the font and draws the string, and paste it before sending the buffer. I will use a smaller font and actually move it more to the top, so the Y position will be 7. After restarting the simulation, there is a text being drawn on the top left corners, so it will be easier to judge what's going on as we access this memory. So let's actually do that. Let's copy a few bytes from the frame buffer and see what's in there. We will create a new helper variable called copied frame buffer, and that will be the array that will for now hold 8 bytes. And we want to copy those 8 bytes from the frame buffer, so after we draw everything, we want to copy the first 8 bytes using the memcopy function. And this function requires 3 parameters. The first one is the destination, which is of course our copied frame buffer. The second one is the source, which is the frame buffer from the U8G2 library. Again, in the U8G2 reference, we can get this by calling getBufferPointer. So we'll say U8G2.getBufferPointer. And the third one is the number of bytes, in our case 8 bytes. We want to see what's in those bytes, so we'll create a simple loop. And we want to print the content using the serial print line function. Before calling the function, we need to start the serial communication by calling serial begin. So I'll copy this into our setup function. And then we can call the serial print line function. And as you can see, it has the optional format. And we can use this to print the value in the binary format. So I'll copy this line, paste it in our loop. And we want to print the value of the copied frame buffer of the index I. Since this area is not changing, we don't need to print this 10 times a second, so I'll most likely just include some very long delay, I don't know, like 50 seconds, so it's not flooding the output. And after restarting the simulation, we can see some values. However, it's not very readable because it just gets cropped, it doesn't include the leading zeros, so it's very hard to read. So instead of using the built-in format, let's create our own way to print binary values. For that, we will use the Arduino bitread function that reads a bit from some value, so we need another loop inside our loop. And let's just change the variable name to j and add the if statement. So if the bit rate of our copied frame buffer on the position of I and the bit j equals 1, in that case we'll print, for example, a capital X. Otherwise we'll print some different character, for example a dot, so something very small, so there is a visual difference between the zeros and ones. Let's print an empty line after every byte, like so, and restart the simulation. And now we see something more readable that actually looks like pixels. However, it doesn't resemble the top left corner of the display very much, because you can see we have 8 empty pixels, but we see 0, 6 ones and 0. And after a close inspection, you can actually see that the first line in our output is actually the first column in the display. So in order to use those values for custom characters, we first need to transpose the array. However, before we do so, we have another problem that is unfortunately not visible on this emulator, but it's very obvious once you copy the code into Arduino IDE and compile the code by clicking this verify button. And this is the problem. So currently we are using 94% of the dynamic memory, which is of course a problem because we will need more stuff for the 16x2 character display. We will need some helper variables for those characters. And it's just a question of time until our sketch will run somehow strangely or actually not run at all. And the reason for using so much memory has to do a lot with using a full frame buffer for the display. So for the display size 128 by 64 pixels, we need 1024 bytes, which is actually the half of the available memory. Arduino UNO only has 2 kilobytes of dynamic memory. And as usual, there are multiple ways how to solve this. We could be, for example, more conscious about the variable types, so you can see that the byte takes 1 byte, the integer takes 2 bytes, and the float takes 4 bytes. So in our code, one example is storing 2D positions of the 3D cube using the integer value, but since the point will be drawn on the display, and the display is only 128 by 64 pixels, we can as well go with byte, because the byte goes from 0 to 255, and we will never get bigger value for the 2D position. However, this will only get us so far, and after all, we don't have that many variables defined in our code. Another option is to go with smaller display, display. Now this simulator only supports this 120 by 64 pixel display, but you can get the display with the same or very similar chip in the resolution of 128 by 32 pixels. And in that case, of course, the full frame buffer will be half the size, only 512 bytes. I can still run it in the emulator. You can see only half of the screen is being updated. That's expected because now we are defining the frame buffer to be only 128 by 32 pixels. And again, that should be fine because the cube will be much smaller. That said, I think that the best solution for this case will be to actually go back to the page drawing method. So in the UAG2 setup, I will search for 128 by 64 pixel resolution, SSD 1306, and my display is no name, so this one. And I'm looking for the hardware I2C connection with the number 1 inside, so this one means page buffer mode, and I think that this line will do it. So I will just copy this into our code, use this as the initialization, make sure that I type in U8G2, comment out the previous one. The rotation will be R0, and I don't need to define reset clock and data because those are the default lines for the hardware I2C. So just comment out this comment, and what I need to do is of course stick back to the drawing loop. So I need this first page and the next page. So I just copy this one instead of clearing the buffer. So here, as we are clearing the buffer, instead we will create a new loop, and we want to jump into the next page like so. So instead of sending the buffer, I will finish the loop, and now this will update the display by 128 by 8 pixel segments, those individual pages. Now as I restart the simulation, you can see that now it reports all the pixels as zeros. And again, that's because the display is now being drawn by pages, and page is 128 by 8 pixels, so we have 8 different pages. And in this loop, we draw everything, and then we look for the pixels, which means that we look on the last page, which is this last section of the display, and obviously there is nothing on the left side. So what we need to do is we need to copy the buffer only for certain pages, and in this case we only want to copy it for page number 0 or for the first page. So let's create a new helper variable that will keep the track of the current page that is being drawn. So up here I will create a new variable that I will call U8G2 current page. I can set it to 0, but what I will do is I'll of course set it to 0 when we jump to the first page in our loop. So after we call the first page, I will reset the current page to 0, and after we draw the page, we will increment this value. So down here, I will increment the value of the current page by 1. Now before we do so, we want to of course copy the content, but only if the current page is 0. So I will say if the current page is 0, then I want to copy the content of the current page. So I'll copy this section into our drawing section. And indeed, now we are back and seeing the content of the top left area of the display. Let's talk about how many pixels we actually need for our 16 by 2 character display. And this is a different project from a different video, but as I zoom in as much as I can, you can see that every digit has 5 by 8 pixels. Now if you look closely, there is actually like almost 1 pixel gap in between those individual elements, in between those individual characters. So there are 2 ways how to handle this. We can either say that this gap is in here, so we will count with this gap, but we'll actually not draw anything because you cannot draw inside the gap, and in that case we will need 23 by 17 pixels. The other way is to ignore the gap and only count with the visible pixels, and in that case we will need 20 by 16 pixels. And that's actually the way how I will do this. Originally I was counting with those gaps, but it wasn't looking so nice, quite surprisingly. So now we will just go with the visible pixels, and again we'll only need 20 by 16 pixels, which is kind of nice because for the page drawing inside the UAG, one page has the 8 pixel height, so we'll need to access 2 different pages to get the content. So let's do that. Let's copy 20 by 16 pixels, which is 20 by 16 bits, which is 20 by 2 bytes. And 20 by 2 is 40, so we need to increase the size of our copied frame buffer from 8 up to 40. Then inside our loop, we will not copy 8, but we will copy 20 bytes. And let's of course also increase the loop to go from 0 to 20. We can now see that we have 20 pixels. Obviously this is still being flipped, so let's just try to fix it. And just to imagine what's going on, I probably want to change the variable names inside our loops to be x and y. So the x will refer to the x position and the y will refer to the y position, just like that. And then inside the bit read, I will of course read the frame buffer x and the bit y. And I want to switch the order of the loops. So first I will go for every y, and then I will go from every x, just like that. And as I restart the simulation, now the array is being transposed, so you can see the hello message, actually just the hell, the way it should be. Now what we want to do is to copy first 20 bytes from the first page, and then first 20 bytes from the second page. So I want to change the if statement saying if the page is 0 or if the page is 1. And for the page 1, we want to store those 20 bytes in the second half of the copied frame buffer array. So for the page 1, we want to start at copied frame buffer at the position 20. For that, we need to get the address of this variable, and we get this by typing ampersand. And we want to get the address of the item number 0 for page 0 and 20 for page number 1. So all we can do is to use the index of the current page times 20 for getting the address. And then inside our loop, we want to of course read the copied frame buffer of the index x plus current page times 20. And as I restart the simulation, we see the word hell, but we don't see anything on the second line, and that's pretty much because we don't have anything on the second line. So let's just quickly update drawing the strings and draw something on the second line as well. So for example, hello without, extra L, word, maybe like this. And indeed we see all those pixels. So we see 20 by 16 pixels that are copied from the frame buffer from the U8G2 library. Now before turning this into custom characters for the LCD display, I want to store every line as a new variable. And just because we have 20 pixels, 20 values, we cannot use integer variable because that one only has 2 bytes. So we have to use something with 4 bytes, for example, unsigned long. So I'll create a new variable of the time unsigned long and call this buffer lines. And we need 16 different lines. And inside our loop, instead of printing the values, we want to actually store it inside our new variable. And for that, we will use the function bit set that sets the bit to 1 for on a certain position for a certain variable. So inside here, instead of printing x, I want to set the bit set of the variable buffer lines. And the index will be y and the bit will be x. Similarly, for setting bit to 0, we can use the function bit clear, and again that sets the bit to 0 for bit n for the variable x. So inside here, instead of bit set, we will set bit clear with the same parameters. Now the y value only goes from 0 to 8 and we have 16 lines. So we want to account also for the second line, and we will do this by saying y plus current page times 8. So it will be increased by 8 on the second line. And we will do this for both bit set and bit clear. Let's just quickly copy the loops and print out the content of the variable buffer lines, just to make sure that it includes what it should include. And since this is unsigned long, it's made from 4 bytes, which means that the x could go from 0 to 32, and the y is 0 to 16 because we have 16 lines. The index is y and the bit is x. And since the content looks correct, we can move on to the next step, which will be adding the 16:2 character display. And that's actually very simple. I will stop the simulation from running, make it maybe smaller so I can see the Arduino as well as the display, and click the plus button and add the 16:2 in the I2C version. Now because the OLED display is also I2C, it will be sharing the same wires, the same connection. So in this case the ground will also go to ground, which is this black one. The VCC will go to 5 volts. Then the SDA will go to the SDA pin, which is the A4. You can see it's being highlighted for us. And finally, the SCL serial clock will go to A5. Again, it's being highlighted. If I want, I can click on the wire and change the color. And maybe let's use the same colors as I used for the OLED display, so blue and purple. Since I have a lot of projects on my channel using the 16:2 character display, I will use one of those as a baseline, so for example this one. And from here I will borrow the initialization, and of course we need to include the library, so I'll copy those 2 lines into our code right on top. And we need to also add this library using the library manager, so I'll click the plus button and type in liquid crystal, and I will select the liquid crystal I2C library. Jump back to our code and jump back to here and find out the setup function, and there are a few things that we need to do. We need to initialize the LCD and we need to turn on the backlight. You can see I have some code for defining custom characters, but let's just skip this for now. So I'll just copy this piece into our setup function in here. Again, I don't need to set up custom characters at this point. I only want to initialize the display, set the backlight, and then I want to print some things. So in here, I will find some printing, which is setting the cursor and printing some text. So I'll copy those 2 lines into our code. And after everything is done, I want to print, for example, string hello world. Set the cursor to 0, 0, which is top left corner, restart the simulation, and now we see a string being displayed on the LCD display, which means that it works. Obviously at this point we are not taking anything from the OLED display, we are just sending text. We can also use my other project to find out how a custom character is being defined. So if I scroll up, you can see I have quite a lot of different arrays which are holding the content of those individual characters. And again, we have 8 different lines, so 8 different bytes and 5 different pixels. So even when a byte includes 8 different bits, we are only defining 5 of those because again, that's the width of the one character. After I have this array defined, I can call the LCD create character function. That one requires 2 parameters. The first one is the position, and it can go from 0 to 7, so we can have up to 8 custom characters, and then the array which holds the individual pixels. To print the character, we can either use the function print or write. And the difference is that the print requires a string, while the write only requires 1 character number. The reason why we cannot use the print function all the time is because a special character with the number of 0 actually has the value of 0, and the value of 0 in the ASCII table means the end of the string. So if we include the character number 0, the null character in our string, it will terminate the string, it will think that this is the end of the string. So if we want to show a custom character number 0, we have to use the write function, which is quite unfortunate, but that's the only way how to do it. So let's go back to our project and try to define those characters. So first things first, we probably need a helper array to hold those individual pixels. So up here, I'll create a new variable that I will call LCD custom character, and that will be the array of bytes. And again, we have 8 lines, so we need 8 different items. And then down here, we want to set the content of those pixels based on the value of the buffer lines. So we will say that the LCD custom character equals the buffer line. And of course, we need to put it inside the loop. So I'll create a quick loop. And the index will be I for both. And after we have some content in this array, let's create a custom character calling the LCD create character function. So down here, I'll call create character on the position 0, and I will use the LCD custom character array for defining the character. Set cursor to 0, 0, and instead of printing the hello world, I will write the custom character 0, which is this line. So I'll just put it in there and restart the simulation. And finally, we can see a letter H, which is matching the letter H on the left side on the OLED display, but let's not celebrate yet. Let's try another piece of the code. So let's try to show the second character, which will be the letter E. And let's actually talk about how this line works. So the LCD custom character is type of byte, which means that it takes only 1 byte, while the buffer lines is type of unsigned long, which means that it takes 4 bytes, so 32 bits. So this is only 8 bits. This is 32 bits. If I show the output, if I show the content of the buffer lines, we are basically taking first 8 bits, like so those 8 bits, and this is just not being used. So what we want to do is we want to take next piece, which will be of course offset by 5 bits. So I want to bit offset everything to right side by 5. And let's restart this and see if we get the letter E. And that's almost the case. I say almost because it looks to be flipped, right? It's a letter E, but somehow it's being flipped. And the reason for this is because we are storing those variables in the buffer lines, starting from the left side, going to the right side. But actually what's happening under the hood is that this value should be stored from the right side to the left side. So it's a question of the byte order of the least significant bit versus the most significant bit. So what we want to do, as we are storing this value inside the array, we don't want to go from the left side to the right side, but we actually want to go from the right side to the left side. And that's happening in here in this loop function. So what we want to do, instead of storing this on the position X, which is the position of the bit, we want to say I want to go from the right side simply by saying 31 minus X. So 31 minus X for both, setting the bit to either 0 or 1. And now as I restart a simulation, 2 things will happen. The first thing is that the content of the buffer line seems to be flipped, so it goes from the right side to the left side. That's actually what we wanted. The second thing is that we don't see anything on the LCD display, and that's expected as well because we are reading the first 8 bits from the content, and there's actually nothing in there, everything is empty. So we want to offset this even more, and we have 32 bits, and I only want the last 5 bits, which means that I need to offset it by 32 minus 5, which is 27. So let's offset it by 27 and restart it again. So now we see letter H, but it's not being flipped, although it's very hard to judge from the letter H because it's being symmetrical, but we can continue like this and we can copy this loop one more time, and instead of bit shifting it by 27, we will bit shift it by 27 minus 5 and create a new custom character on position number 1 and set the cursor to be position number 1 and 0 and print byte 1. And while we are doing this, let's just copy it 2 more times before we turn this into a real loop. So minus 5 and minus 5 minus 5. This will be character number 2 and character number 3, and print all 4 characters on the display. And now the word hello on the LCD display looks very similar to the word hello on the OLED display. If you want to show the second line, we just need to add the number 8 to the index of the buffer lines. Again, there are 16 lines, and that will show the word word. So before showing the real 3D cube, we just need to turn this into one loop instead of copying the code all over again. Let's start by commenting out the old code for creating us custom characters and create a new loop for every single character. And I'm using the counter named character ID. Then select any of the previous code and copy it inside our loop. And just to make things clear, I'll probably rename the I to maybe something like character line. We want to create a custom character on the position of character ID. And of course we need to change few of the parameters. So for the first 4 characters, we want to set the buffer line of the index I, or actually character line. For the next 4, we want to set the index to be character line plus 8. As for the byte shifting, it should be 0, minus 5, minus 10, and minus 15, and then it should repeat itself for the next 4 characters. And let's, for example, use Excel to visualize those equations. So we have the character ID, which goes from 0 to 7, that's our main loop, and we want to set the buffer offset, which should be 0 for the first 4 characters and 8 for the next 4 characters. What we can probably do is we can probably divide the character ID by 4, And while this will give us decimal numbers in Excel, if you divide integer by integer in Arduino, it will give you the integer value. So we can fix this in Excel by saying integer function. And you can see that now it switches between 0 and 1. So all we need to do is to multiply it by 8. And just like that, we have the first equation, which I can maybe copy it up here so we can see it. And then we need the bit shift, and that should be 0, minus 5, minus 10, minus 15. And then it repeats itself, so minus 5, minus 10, and minus 15. And usually when something is repeating, it's a good idea to use the modulo function. So I will say equals character ID modulo 4. And in Arduino, you use the percentage sign, but in Excel, you have to use the modulo function, so MOD for modulo, and the divisor will be 4. And as I expand this, you can see that it repeats 0, 1, 2, 3, 0, 1, 2, 3. So it's just a matter of multiplying this by minus 5 and we get our equation. So again, I'll just copy it outside so we can easily see what's going on. And with that in mind, we can apply those equations to our code. So the buffer line index will be character line plus the character ID divided by 4 and multiplied by 8. And the bit offset will be 27 minus the character ID modulo 4 multiplied by 5. And as I restart the simulation, we can see the first line. We've actually defined all 8 custom characters. We are just not printing those yet. So I'll just copy this piece of code and update it to also print other 4 characters. And so now it's finally the time to say goodbye to our hello world message and try to show the 3D cube. Before we do so, let's just get rid of all the printing because we'll be updating the display 60 times per second, or actually very fast. So we don't want to flood the output with some values. Instead of deleting, I will probably just comment out the printing the content of the variable buffer lines. And there is one more print in here which I will comment out as well. We also don't need any delay at this point, and we don't need to draw the text to the top left corner of the LCD. Let's make the cube much smaller and move it to the left top corner of the OLED display. So the size being set up here is a cube size, and currently it's oscillating with time, but let's just have it at some predefined value, for example 17. And the position is set down here. So I want to move the points I0 and I1. The second index of 0 is the X position, so let's just move it to, for example, by minus 57. Second index of 1 is Y position, and we'll move it by minus 24. And those are just values that I've tried and they work well. So we have a rotating cube, but as you can see, it's blinking quite a lot. And even when for the real LCD it's not very visible, it's quite distracting here in the emulator. And the main reason for this is we are writing those characters to the display every frame, which is not really needed. We only need to do it one time because after that we are just updating the content of those custom characters. We are not changing the position. So what I can do is I can just copy everything, or actually cut everything and paste it in the setup function. And of course get rid of those comments which don't make any sense. And after restarting the simulation, we see a rotating 3D cube. But let's just not celebrate yet. Let's say we also want to change the size of the cube as we rotate it, and we can use the very same equation that was there previously, but we'll just make it much smaller. So for example 20 plus minus 6. And as I do so, we will see what happens. Suddenly it looks very strange and very wrong, and that's because the U8G library particular doesn't like if you draw stuff outside of the boundaries of the display, especially if you want to draw to the negative values. So we can either say that we will not change the size of the cube, or we have to do it in a different way. And the different way might be to keep the cube in the center of the screen, and instead of reading the pixel from the top left corner, we will read the pixels from the center of the display. Moving the cube back to the center is simple, we just don't add those values to calculate the 2D positions. So now the cube is not on pages 0 and 1, but it's on pages 3 and 4. So I'll just change those values in the code, so 3 and 4. And since we are using this variable in our code, we have to subtract 3 from this in our 4 places. However, this change alone is not enough. We are still reading the pixels from the left part of the page, while the content, the 3D cube, is in the middle of the page, which means that we need to offset it by 54 pixels to the right side. And we do it as we copy the memory from the frame buffer, so the get buffer pointer gives us the first pixel, and we need to offset it by 54. And now we finally see the rotating and scaling cube on both the OLED display as well as the LCD display. Before running this on the Arduino, let's just quickly update the code to show the 3D cube on the LCD display multiple times. And since we have 16 characters per one line, we can either show 4 different cubes, or we can show 3 cubes with some spacing around them. And I will probably include the spaces. And I know that you can probably write this loop in a much better way, but I couldn't wait to get this running on the Arduino, so here it is what it is. It's not perfect, but it runs. It displays 3 rotating cubes on the LCD display. So let's see how you can run the same sketch on the real Arduino with the real displays. Inside the Arduino IDE, I will paste the code from the work with sketch and then go to the sketch, include library and manage libraries. And make sure I have both the U8G2 library installed as well as the Liquid Crystal I2C. Select the correct board, which in my case is the board Arduino UNO, and of course the correct port, which will be different in your case, and then click the upload button. As for the connection, it's the same as on the walkway sketch, so the ground goes to ground, the power goes to 5 volts, and the SDA, which is serial data, goes to either a dedicated SDA pin or pin A4, and SCL, which is a serial clock, goes to either the dedicated SCL pin or pin A5. And so here are the 3D cubes spinning on the LCD display. Now, if you don't see anything on the display, it's possible that your display maybe has a different I2C address. In that case, you might want to run the I2C scanner first, and that's described in many of my other videos, links are in the description. Thankfully, all my displays, including the VFD display as well as the OLED display, share the same I2C address. If you want to know more about character displays or OLED displays or both, please watch this video next. If you have any comments or questions, please put those out in the comment section. And that's it for today. Thank you very much for watching, and I hope to see you soon. Thanks and bye.